On April 13th, 2029, something will cross the sky that has never happened in the entire span of human civilization. A 340-meter asteroid will pass closer to Earth than the satellites we use to navigate, communicate, and watch the weather. Not a near miss in astronomical terms. Close enough that people in Europe and Africa will be able to watch it move with the naked eye, a point of light drifting visibly against the stars in real time. Its name is Apophis, and the closer scientists look, the less they understand it. The story of Apophis begins with a moment of genuine alarm. In December 2004, astronomers at Kitt Peak Observatory in Arizona detected a new object in the inner solar system. They ran the orbital calculations. Then they ran them again. The numbers kept coming back wrong, or rather terrifyingly right. For a few days, the probability of impact in 2029 climbed to nearly 3%. That is extraordinarily high for a rock this size. 3% doesn't sound like much until you consider that a 340-meter impactor would release energy equivalent to roughly 1,000 nuclear warheads, enough to flatten a region the size of France. The alert was real. The Torino scale, the system astronomers use to communicate impact threat to the public, briefly rated Apophis a 4 out of 10, the highest rating ever assigned to any object before or since. Observatories around the world shifted to track it. More data came in. The orbit refined. The impact probability for 2029 collapsed to 0, but the 2029 close approach itself remained, closer than any object of this size in recorded history. Certain and locked in, a gravitational appointment already written into the physics. 31,000 kilometers. That is how close Apophis will come to Earth's surface. The ring of geostationary satellites, the belt that carries GPS, television broadcasts, and global communications, orbits at 35,000 kilometers. Apophis passes inside that ring. It will cross through a volume of space that humanity has filled with hardware, threading through the infrastructure of modern civilization without touching any of it, as far as anyone can calculate. The margin feels wide until you remember it is being calculated across 25 years of accumulated orbital uncertainty. Here is where the strangeness begins. When astronomers started measuring Apophis in detail, using radar, spectroscopy, and light curve analysis, they found an object that doesn't behave the way a solid rock should. Its density is unusually low, not low like pumice. Low like a loosely packed pile of rubble held together mostly by its own weak gravity and some internal cohesion no one fully understands. The technical term is rubble-pile, and it changes almost everything about how this encounter is supposed to go. A rubble-pile is not a single object in any conventional sense. It is a collection of fragments, boulders, gravel, dust, aggregated over billions of years, bound together by gravity rather than structural integrity. Hit a solid rock hard enough and it shatters cleanly. A rubble pile absorbs the energy differently, shifts, reshapes. Subject it to strong tidal forces and it may deform, shed material, reconfigure its spin, or in extreme cases begin to pull apart. The 2029 flyby will subject Apophis to tidal forces from Earth's gravity that it has not experienced in millions of years, possibly ever. The shape makes this harder to model. Apophis is not a sphere or a potato-shaped lump. Radar imaging has revealed something stranger. Two lobes, connected by a narrow neck, like two objects that slowly merged long ago and never quite finished the job. That neck is a structural weak point. Under tidal stress, it is the place most likely to fail first. Models suggest the deformation during the 2029 flyby will be measurable. But whether measurable means a few millimeters of internal shifting or something more dramatic depends entirely on the internal structure, which no one can directly observe from Earth. And then there is the spin. Apophis does not rotate cleanly on a single axis the way a well-behaved asteroid should. It tumbles, what planetary scientists call non-principal axis rotation, wobbling as it moves, like a football thrown by someone who never quite mastered the spiral. This kind of spin is unusual. It can be caused by a previous impact, a gravitational interaction, or thermal effects acting over long periods. Whatever caused it, it complicates every calculation. The rotation state going into the flyby affects how tidal forces distribute across the body. Small differences in tumble become large differences in outcome. There is a term for what Earth will do to Apophis during the flyby: tidal disruption. It is the same force that tears comets apart when they pass too close to a planet, most famously Comet Shoemaker-Levy 9, which Jupiter shredded into a chain of fragments before they rained down on the planet in 1994. Apophis will not come close enough for catastrophic disruption, but it will experience tidal stress strong enough to potentially alter its rotation, shift material on its surface, trigger small landslides of loose regolith, and possibly change its shape in ways detectable from Earth. The asteroid that leaves the encounter may be observably different from the one that enters it. That difference matters for a reason beyond scientific curiosity. After the 2029 flyby, Earth's gravity will have changed Apophis's orbit. The new trajectory is already calculated, and it does not pose a threat for at least a century. But the Yarkovsky effect, a subtle force generated by heat radiating off the asteroid's surface, depends on the rotation state. If the tumble changes during the flyby, the long-term trajectory changes with it. Small errors compound over decades. A 2036 impact was already ruled out, but the calculations for later encounters, 2068 in particular, depend on knowing precisely how Apophis spins after 2029, which means the flyby itself is the experiment. The scientific response is unlike anything assembled for a planetary event in recent memory. OSIRIS-APEX, NASA's asteroid probe, is already on its way to rendezvous with Apophis during the flyby. It will orbit the asteroid before, during, and after the encounter, watching in real time as Earth's gravity does its work. The European Space Agency, JAXA, and observatories on every continent are coordinating observations. For roughly a week in April 2029, Apophis will be the most studied object in the solar system after Earth itself. OSIRIS-APEX was not built for this mission. It was OSIRIS-REx, which had already collected a sample from the asteroid Bennu and delivered it to Earth in 2023. After the sample capsule was released, the spacecraft had fuel remaining and a working instrument suite. NASA redirected it to Apophis. It arrives in 2029 with enough propellant to match Apophis's orbit and stay close during the encounter. Close enough to detect surface changes, monitor the rotation state in real time, and document whatever Earth's gravity does to an object that has been tumbling through the solar system undisturbed for billions of years. What they are hoping to catch is not a catastrophe. The probability of significant structural disruption is low. What they are hoping to catch is the subtler version. The millimeter-scale surface movement, the slight shift in rotation period, the small redistribution of mass inside a loosely packed body responding to forces it has never felt before. These are the things that would answer the deeper question: how does a rubble pile actually hold together, and what does it take to start pulling one apart? That question matters far beyond Apophis. Most of the asteroids large enough to pose a serious threat to Earth are believed to be rubble piles. If humanity ever needs to deflect one, using a kinetic impactor, a gravity tractor, or any method currently under development, the internal structure of the target determines whether the deflection works or simply kicks the rubble into a slightly different configuration. The DART mission tested deflection on a solid moon of a solid asteroid. Apophis is a different class of object, and 2029 is the only chance in any living person's lifetime to watch gravity stress one of them at close range. April 13th, 2029. The date is not arbitrary, it is a Friday. Apophis was discovered close enough to its first predicted impact date that the mythology was hard to avoid. The Egyptian god of chaos and darkness, destroyer of worlds. The name stuck. In the end, the asteroid named for chaos will not bring any. It will pass through our satellite belt, bend slightly under Earth's gravity, and continue into the outer solar system, trailing a faint uncertainty about what it has become. For a few hours on that Friday, every telescope that can be pointed at it will be. And whatever is strange about Apophis, the low density, the lobed shape, the tumbling spin, will either get stranger or begin at last to make sense.